Welcome back, colleagues, astronomers, computer scientists, and fellow professional computer touchers. This is 66 plus 1. This is kind of a cool problem, but it's kind of tough if you don't think about it. It really has a really intuitive solution, but you kind of have to think about it and really kind of put a stepwise, instruction on top of how we traditionally do addition, right? Which can be a little bit confusing to think about, despite what most people think. So, given a non-empty array of decimal digits representing a non-negative integer, so input here are our arrays 1, 2, and 3, representing the number 123. So you can see that the number is broken up into its constituent elements into an array. Increment 1 to the integer. So an array here, which is representing 123 plus 1 is equal to 124. Makes sense, right? The digits are stored such that the most significant digit is at the head of the list. And each element in the array contains a single digit. So that makes sense, right? If you take a look, right, the 0th index of this array is going to be 1, right? That's going to be the hundredths place of this number, right? But if you're going to be adding 1 to the digit, right, you'd want to add it from the other end, right, which would be the end of the array, right? Because if you want to turn 123 to 124, you have to do 1. You just have to get the last element in the array and add 1 to it, right? Makes sense. So you may assume the integer does not contain any leading zeros except the number 0 itself. And what they're saying here is that there's no leading zeros. So if you have 0, you can assume that it's just 0. Then you can add 1 to 0, you get 1. Right? So you might be thinking, right, well, this seems like a really simple problem, right? And so you might say, hey, well, if I have 123, I just have to add 1 to the last element, right? So couldn't I just do digits sub -1, get the last element in digits, and then just do digits sub -1 plus 1, and then return digits, right? And you'll see you might pass the first test case, right? Makes sense. We grab the last digit, we add 1, right? But you'll see that this naive approach quickly will fail. First time doing this problem, by the way, actually true, right? Because look at this. We have 9 here, and it's not so simple to grab the last element, right, in the array and just add 1 to it, right? So it's really not that simple. And so the idea here, right, is to layer a more intuitive answer on top of this, right? And so you could also do another. Oh man, I'm clicking the wrong things. You can also do another thing, right, where you might say, hey, couldn't we just iterate through the list of digits, right? Turn them into an integer some way. Maybe you iterate through it, right? You add them all to a string, then you turn the string into an integer, add 1 to the integer, right? And then you transform it back to a string, back to a list of elements, right? And that seems intuitive at first, but I won't waste the time doing it. But in here, you end up with some kind of tricky caveats to deal with, which are less intuitive. So I'm going to show you a far more intuitive solution, right? And so what I'm going to take you to is Sketchpad, right? So we're taking it back to the basics, okay? So we're just going to do some very simple addition here, right? So let's just humor me for a bit. So we have 124, right? We want to add 1 to 24. What are the literal steps that we have to take to do that? Well, we check the last digit, right? The least significant digit, and we say, hey, is this number a 9? Right? It's not. So we can just say, add 1 to this number and leave the rest alone, right? Kind of like our naive solution here, right? We just look at the last number and we add 1, right? But we just like in the last number, we take a look and we said, hey, whenever there's a 9, things kind of get messed up, right? But you can see here as well. What are the steps we're taking here? 100 plus 1. We're going to say, hey, let's look at the least significant number, 0, right? And say, hey, is it a 9? It's not. So we can just add 1 to it and then use the rest of the numbers as they were. We run into a couple finicky, I guess the other problem case of this, right? Whenever you have 9s, right? So just for a simpler problem first, if we just do 9 plus 1, right? What's the idea here, right? The idea here is that, hey, now you see a 9, right? And you say, hey, if I see a 9, we always turn 9s into 0, right? Because we're using the base 10 system. There's only 10 symbols. The symbols are 0 to 9, right? So we just keep looping around that symbol, that symbol, right? Like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Once you get 9, you go to 0. Once you go to 0, you go to 1, and so on and so forth. So we see a 9 here for the first time, right? We know that every time we see a 9, we instinctively turn it into a 0, right? And what do we do with the 1, right? Well, we usually, right, depending on how you learned addition, you usually add a little plus 1 on top, right? And so what you do there is, right, and then what you would do is you'd go to each remaining number, right, and see, hey, can I add anything? Can I add 1 to the first non-9 number, right? If not, I have to keep saying, hey, is it a 9? If it's not a 9, then we can't add 1 to it, right, without turning it to a 0. So we'll see this here. So 99 plus 1. Well, we said, hey, is the least significant number a 9? It is. What do we do when that happens, right? Everyone knows you instinctively turn it to 0, right? Then you put the 9, right? You put the 1 over the 9, right? Because you have to carry the 1, and you just keep carrying the 1, right? So now you have plus 1, right? But what's cool here with this solution is that the solution is very intuitive, right? We're asking the same questions all the time. Is it a 9? If it's a 9, turn it to a 0, and then go to the next number. So this is a 9. Well, turn it to a 0, right? And then we'll just drop that down, and we add plus 1, right? And then what you notice, right, is that as soon as there's a non-9 number, we can just add it down, right? In this case here, right, everyone knows that there's kind of a secret hidden 0 here, right? And so what you're technically doing is adding 0 to 1, right? And you get 100. And so that's a very simple way that we can kind of take this solution to the game board, right? So we can kind of visualize this like this. Hey, we're just going to say, hey, the problem's called plus 1. We're always going to be adding 1, right? So why can't we just add it like we add numbers? We're just going to say, hey, turn all subsequent 9s into 0s. And the first time you see a non-9 number, add 1 to it, right? And that's literally what we do when we add. If you have 1, let's just say 98, oops, I butchered that one, plus 1, right? This is not a 9. There's nothing to turn to a 9 here, right? We say whenever we see the first, we always said if there's a 9 at the end, right, turn it to a 0. If not, if it's a non-9 number, then add 1 to it and just return the rest of the numbers as they were. What's the answer here? 199. But as soon as you run into something like 209, and we say, hey, add 1 here, or something, I guess, a little bit more, 299 plus 1, make sure you guys can see that. I think you can. We just say, hey, is the number we're currently at, which is the least significant number, is it a 9? We'll turn it to 0, right? We're just going to turn it to 0. And see, seeing why we're always turning subsequent 9s into 0s, right, is because we're simulating carrying the 1, right? Because if you're carrying the 1, the 1's above the 9, right? And it's the same thing over and over again. If you see a 9, turn it to a 0. The first time you see a non-9 number, add 1 to it. 300. And so now we can kind of jump to the algorithm, right? So we can take that. We said, hey, loop over digits. If we see a 9, if we see a 9, right, we said turn it to 0, right? If else, right, it's a non-9 number, right? What did we say we were going to do when that happens, right? If it's a non-9 number, we just said, dude, add 1 to it and return it. The solution's done, right? If you see a 9, turn it to a 0, turn it to a 0. If you see a non-9 number, add 1 to it, and then return it. We're done at 300, right? And so that's kind of the algorithm, right? With a caveat, but I'll show you what that looks like. So we said loop over digits, right? But we said in reverse, right? Because we have to start at the least significant digit. Least significant digit, right, being the 1's place, 10's place, 100's place, and so on and so forth. How do we do that? Well, our index is going to start at the length of digits, right? And we're just going to say, hey, while index is greater than or equal to 0, right? And at the bottom of our while loop, we're just going to say index is minus equal 1, right? Because we're going to be linearly iterating towards 0, which is a 0th element. Right, we said, hey, if we see a 9, turn it to a 0. How do we check if we see a 9? Well, we have the index, so we say if digits sub index equal 9, right? We said, what do we do if we find a 9? Turn it to a 0. Bro, turn this to a 0, right? And then we keep going, right? We said else it's not a 9, it's a non-9 number, right? So add 1 to it. So digits sub index is going to be equal to digits subindex plus 1, right? But, right, when we said once we find a non-9 number, right, we know we're done, right? Because we can't carry the 1 any further, right? So we have to return our answer here, right? Because that's one of our exit cases, right? Once you're able to successfully add the 1 without having to propagate that 1 over and over again, you're done, right? And I think we can run this here, right? And we'll get kind of a rudimentary answer for now. List index is out of range. Oh, I think we have to do -1. There we go. So we get the answer for now because the first index in the list is capacity -1. And so we get a rudimentary answer, right? And so what you notice, if we run this, right, we're going to fail on a very specific case. Now you must be wondering, why do we fail on this case, right? We have 9, we have 9, but we end up with a 0 somehow, right? We're supposed to end up with 10 because 9 plus 1 is 10. Why does that happen, right? So if we go back to our case here, right, if we do our algorithm like we just did up here, we say 9 plus 1. Oh, let me do it higher, actually. We're going to say, if we do, ooh, that's bright. If we do, but it's fine. If we do 9, right, plus 1, what happens, right? Well, we said that in our algorithm, right, that we would literally search for every 9, turn it to a 0. Well, let's do that. And we're starting from the least significant digit, right, which is 9 here. Well, let's turn it to a 0. So, oops. So we turned it to a 0, right? That's what's supposed to happen. That's what we said our algorithm was going to do, right? So this gets us to the one edge case of our algorithm, right? The only way you make it out of this loop, right, because you get out of this loop once you reach the end, right? But you exit and return an actual answer, right? Once you're able to stop that infinite propagation of the 1, right? You added 1 to a couple 9s, so we turn them to zeros. The first non-9 number we found, we added 1 to it, and we're good, right? Why is it that when we do get to 9, our problem begins, right? It's because the only way to get out of this is once you stop propagating the 1. So what do you have to do here, right? What does our edge case look like? The problem, right, our edge case in our algorithm that we're not covering, right, is whenever our algorithm contains only subsequent 9s, right, you'll see that we'll always run into this problem. So no matter how many 9s you have, if we try to add 1 to them like the algorithm wants us to, right, our algorithm says, hey, turn all 9s to zeros, right? Turn all 9s to zeros, right? And so this is why we always end up with zeros, right? And so the solution to this, right, is the fact that if we made it out of this loop, right, if we make it outside of the while loop, we made it, let me close this and this, we made it, move this over a little bit. So we made it outside of the while loop, right? How do we, so if we made it outside of the while loop, right, what does that mean? What does that mean? It means that our input after transforming all 9s to zeros is all zeros. And if our input after transforming all 9s to zeros is all zeros, what does that mean? It means that our input was all subsequent 9s, right? And once you have subsequent 9s, right, what do you have to do? Well, you have to go past the most significant digit, right, and add 1. So you have 99 plus 1. You're only working with the 1s in the tens place. Now you have to add 1 to the hundreds place, right? And so how do we fix that? It's a very simple fix. We just say digits.insert at the 0th index, insert a 1, right? Because 9 plus 1, if we turn all the zeros, if we turn all the 9s to zeros, we append a 1 to the front, we get 10. If we have 999, we turn all the zeros to 1s, we get 3 zeros. We say insert a 1 at the front, right? And so that's what we're going to do. And if you take a look here, we'll run the program now, and it works, right? So what's the time and the space complexity here? The time complexity here, our operations are linked to how many number of elements are in the list. So it's going to be linear time, right, where n is the number of elements in the list, which directly correlates to how many digits that we have to look through. It's oftentimes going to be a lot less than n, but we're just saying that because that's the worst case, right? In the case that it's all n, I mean, it's all 9, right? So what's our space complexity, right? So you might be thinking, hey, we're not really doing anything crazy. It's probably constant space, right? Wrong. right? Because what's going on here, right? So our worst case scenario, right, or I guess our best case or average case scenario, right, is constant space, right? Because we turn all 9s to 0s, so we're doing an in-place operation here, and then we increment the first non-9 number, so it's also kind of an in-place operation, right? So we don't modify any of the space that we're using, right? And we're not creating any more space, right? But as soon as we have to do with all 9s, our worst case changes, right? And so we have to insert an element to the front, right? So the space that we'll be taking up will be linear space. And so that is 66 plus 1.